Hi, today we're going to take a look at section 7.4, which deals with what we call separable differential equations. Just to kind of lay some context here, let's recall some of the stuff we've talked about when we talk about differential equations. For example, suppose we have some scenarios where we're not able to symbolically find a differential equation, but we use slope fields as a way to get approximate value or approximate functions that will work, even though they may not be expressed as a function. So for example, suppose I'm going to start with a differential equation of the form dy dt, I'm going to use x instead of t, but dy dx is equal to, say, x squared minus y squared. Okay, so we can try to solve this differential equation, use our differential equation solver. So let me do that. Let me go to Menu, down to Calculus, and here the differential equation solver. Okay, my equation is, and again, if you look down here, you can see that we need to use y prime equals that sort of notation. So I'm going to say y prime equals x squared minus y squared. Need to tell it the independent variable, in this case that's x, the dependent variable, which is y. And let me go down here and say OK. We're going to hit enter. And you'll notice that the machine is basically feeding me back what I gave it, meaning it doesn't know how to find a solution, in other words, a function that satisfies this differential equation. So, what have we done in the past? Well, we can always use slope fields as a way to get a handle on it. So what I've done here is I've actually plotted it. If you want to see what I've plotted here, you'll see that actually here we're calling it y1 instead of y. But y1 prime is equal to x squared minus y1 squared. So it's generating, basically, it's plugging in x and y coordinates, plugs them into this expression right here, and then plots a slope. So for example, just to refresh, let's say I look at 1 down here. Okay, so if I look at 1, if I plug an x coordinate of 1 and a y coordinate of 1 in here, I'm going to get, if we look at the point 1, 1, then dy dx would end up equaling 1 squared minus 1 squared, which is 0. And you'll see that on my graph, right about here, where that little point is, that initial condition point that I gave it, actually has a slope of 0. Okay, there's a flat spot right there. So it's a local min, for example. If I'd used a different value, so let's say we use, let's say, 1, 2, that means that the slope we'll use this notation. So I plug a 1 in here. So I'd have 1 squared minus 2 squared. So this would be 1 minus 4, which is negative 3. So this thing would have a slope of negative 3. So if I double click on this guy and I change my initial condition to 1, 2, you'll see it move. And now you see the big dot that's showing up right here, my initial condition, has a slope of negative 3 right there. And the slope field is being generated by looking at a particular x and y, or an x coordinate, and basically putting the slope, depending on what the y coordinate is, vertically up and down. So this is basically a solution to this differential equation given these two specific values. Now, we're having to do this, we're having to use this method. Actually, the machine is using what's called Eulers Method, which basically is a way of course correcting. You start with an initial, it tells you what the slope is. So in this case, for example, negative 3. So it starts at the point 1, 2. It does a slope of negative 3, so it goes over 1, down 3, approximately, and then it readjusts. So then it computes that new point that it comes up with at that stage by using that projection, plugs it back into the differential equation, gets a new slope, reevaluates it, goes again. So it's like, riding in a ship where you go a little ways, you do a course correction. You go a little ways more, you do a course correction. So it's like stitching together a bunch of little line segments, so to speak, which is why you'll notice that in here, you're starting to see like sparse points. In here, they're a little closer together because there's such a separation because the slope is so steep there that from going from one point to the next, it doesn't actually show a, quote, continuous looking graph. Okay, so this is one way that we can deal with a situation when we can't find a differential equation symbolically, can't find the solution. So what we're going to do in 7.4, though, is we're going to look at when can we actually find these things separately. So let's play around with that just a little bit. So here's what we're going to do. We're going to look at different kinds of differential equations and try to decide whether or not we can actually separate them, separate the variables so that we can actually solve them. That's really going to be the key. So, for example, let's look at dy dt being t times y. Okay, so let's suppose that we have this differential equation and we want to know whether we can solve it or not. We could use our differential equation solver and see if the machine can do it, but what is it different about this one compared to the one we looked at before if this one is indeed solvable? Well, let's think about it. The idea here is we have two different variables. We would like to be able to use the fundamental theorem of calculus, which says I can find an antiderivative pretty easily by using things like the power rule or things we know about the relationship between sine and cosine and their derivatives and so on like that. So here I'm going to try to separate out, which is why we're calling it separable differential equations. I'm going to try to separate the y's and the t's so that all of y's end up on one side and all of t's end up on the other side. Then I can integrate both sides in their respective variables and then come up with a solution. So here's what we're going to do. It looks like my dy is in the numerator here, so I want to try to get all my y's on the left and all my t's on the right. So let's see if there's a way to do that. Well, I can bring my dt up here. So I could say, what if I've got dy over, and I could bring my y down, so I could divide both sides by y, and at the same time multiply both sides by the dt. And I get an equation like this. All I did was rearrange this differential equation. Now you'll notice that I've got my y's on one side, my t's on the other, so now I can actually go ahead and integrate this thing. So that's going to say the integral. And if I want, I can rewrite this as 1 over y dy. And then this one here, I'm going to have the integral of t dt. Now I can integrate both sides with the respective variables and see what I get. Now if you recall, the antiderivative of 1 over y is natural log. So this is going to say that on the left, I end up with natural log of y. And on the right, I simply apply the power rule. And so that's going to be 1/2 t squared. Plus, and then of course, with all of these, there's going to be a constant on both sides because remember, there's if we have two functions that share a derivative, they differ only by a constant. So we're always having a plus c. So if there's a plus c on this side and a plus c on this side, I could throw all those on one side and put them together into one great big constant c. So I'm just going to call that c. That's a c, not an e. I don't want to confuse it. Okay. All right. So, not looking too bad. The problem is I don't really have this thing in terms of y equals. So I'm going to actually take and raise e to both sides. So that's going to say e to the log y is equal to e to the 1/2 t squared plus c. Now, e and natural log are inverse functions, so they undo each other. So that's going to give me basically y on this side. On this side, I have e to the 1/2 t squared plus c. Now again, these are in the exponent, so if I want, I could write that as e to the 1/2 t squared times e to the c if you want. And e to the c, remember c is a constant, so e to the c is just going to be a number. So if I want, I could say, well, let's just call this thing right here something like a. So that would be a times e to the 1/2 t squared. So basically, the idea is that this should satisfy this differential equation. Let's try it. Let's see what's going to happen here. So let's define a function. Let's just call it f. F of t equals a times e to the 1/2 t squared. All right, there we have it. Now let's see if it actually satisfies this differential equation. So let's take its derivative. With respect to t. And I get that expression right there. So a t e to the 1/2 t squared. Now let's actually compute this side. So that's going to be t times the original function, which in this case I'm calling f. And lo and behold, I get this same thing. In other words, that thing equals that thing. And it says true, because it satisfies this differential equation. So this ends up being a solution to the differential equation that we're talking about here. We were able to do this because we were able to separate the two variables that made up the expression for the slope. So the ability to pull them apart is important. What we didn't have in the previous example what was it? I think I called it dy dx equal x squared minus y squared. We didn't have a way to separate the x's from the y's on the, in this case would be the right side, I guess. On the right side of the equation. So the key here is this ability to pull the things apart. So let's take a second and we'll take a look in a minute at preview activity 7.4.1 and see how we can determine whether or not something's separable or not. Okay, so here are the ones from activity 7.4.1. And the question is, can we separate these? Are these separable so that we can solve them? Well, let's look at the first one. It's not too bad. It's kind of like the one we had before. I can bring the y down here and the dt up. So that's going to say that dy over y is going to equal -3 dt. Okay, the nice thing about this is I can integrate both sides of this. This becomes a log. This simply becomes -3t. So that's doable. What about this guy? A little bit different. Here, I don't want to try, if I move this y to the other side, the problem I'd run into is I now have a t and a y on this side. But one thing I can notice is I can factor the t out of both of these. So I can say, dy dt is equal to y times, if I factor a y out of this one, I'm left with t. If I factor a y out of this one, I'm left with 1. And I end up with that, which then says if I bring these down, the dt up here and the y down, I end up again with dy over y is equal to t minus 1 dt. And again, these are both integrable. I can integrate this guy getting a log. This guy is just a polynomial. I can integrate him very easily. So life's pretty good. This one, similarly, I don't have any y's at all involved over here. So I can say dy dt, or dy, is equal to t plus 1 dt. Okay. And that this guy here clearly is a polynomial. It's integrable. This guy is just a constant. Think of it as 1 dy. Integrate that guy and just get y. So life's good. This one here, no way to separate. Okay, we saw this one before. This is our first example that I was using with the graph. So in this case, we've got some things that can be separated, some things that can't. When we can separate them, we can actually try and solve them. So for example, let's take a look at what these guys look like. Let's play around with this guy and see what he looks like. Let me add a new problem. Add a calculator page. And let's do menu, calculus, differential equation solver. Like I said, this one isn't too difficult because we end up with a log here. And so again, since this is going to end up being log y, we're going to have to eventually take e to the power, which is going to make this side here a exponential as well. So let's just put in the differential equation we want. So I'm going to call that y prime equals, I'll start with its original form, t times y minus y. Okay, in this case, my independent variable is t, my dependent variable is y, and I get something of this form. So the solution to this differential equation, again, the c1 here is just referring to an arbitrary constant. So we can call it c if we want, we can call it a, we can do anything we want. So here we're ending up with y is equal to, I'm going to call it a, e to the t squared over 2 minus t. Okay, so there's our solution to that particular differential equation. We can see what it's going to look like. So let's add a graphs page. Oops, pardon me. Let's add a graphs page. Let's go to a differential equation solver. Go to graph entry edit. Oops, there we go, differential equation. Okay, here, now keep in mind, the machine is calling this y1. So instead of y, I'm going to have to call it y1. And also, if I'm going to graph things, my independent variable has to be called x. So I'm going to write this as y1, and this is going to be x squared over 2 minus x. So just keep that in mind. I'm just doing a variable change here. So my original differential equation would be x times y minus y. Oops, and I did it again. I need to call it y1. Okay. And here's what the slope field is going to look like. If I want to change, by the way, I'm going to double click in the white space here. If I want to change how frequently I see field lines, I can go up here to the dot, dot, dot. All right. And I can tab down and say I can also change the window where the plot starts and stops, but I'm just going to put in, instead of a resolution of 14, I'm going to put in, let's put in 30 so we can see a lot of field lines. It slows down the plotting a little bit, but actually it'll allow you to see it a little bit better. Okay, there we go. Okay, so this is what the slope fields look like. So again, keep in mind each of these are like little mini tangent line segments. So if I wanted to, I could give it some initial condition and plot it. I'm just going to change this and plot just this baseline one here. We'll pick a value for A and see what happens. So I'm going to go back to my function plotter. And I'm going to plot the function. Let's pick a value for A. Let's pick like 2. So I'm going to do 2 times e raised to the, and again we have to use x's instead of t's. So I'm going to do x squared over 2 minus x. Okay, and again this number a that I pick will basically shift things around, and it's kind of like the plus c when we did the integration. That's where it came from. But you'll notice that depending on what value I pick for A, it's going to move it a little bit, but you'll notice that this graph is following the slope field lines. So where it crosses the slope field, it's actually matching a slope field line for the slope. If I wanted, I could go in here and change this guy. Let's say I change this to say a 3. Okay, it's going to move. Let's see what's going to happen if I make my initial condition a little bit different. Let's put a negative in here. Let's put -2. Okay. There, I get it down there, but again, it's still following the slope field. So the idea is this is like my plus c, so as I change it, I could put a slider in if I wanted. Actually, let's do that for fun. I'm going to call this A, and the machine's going to ask me if I want a slider, and I'm going to say sure. And here's my slider. Let's make my slider pull on a little bit. Oh, I've got it listed as minus A. I forgot to get rid of that minus sign. Let me get rid of that for a minute. There we go. And now when I pull on the slider, you can see it move. Now it's down below. Okay. And that's going to determine specifically what it is. Okay. And we could do this with all of these. This one here, we actually wouldn't be able to actually plot a function because we can't separate the variables here. But these guys are all separable, so we could solve these differential equations by hand if you wanted, and life would be just fine. Okay. All right. So that's kind of the idea of being able to determine if I can separate something or not. If I can, then I can actually do it by hand and not have to use a differential equation solver. All right, let's take a look at this example where we have dy dx as x over y squared. We're going to take a look at it, solve it by hand. We'll take a look at the plot of it and see how the plot, for example, compares to maybe Eulers Method as a numerical approximation technique when we graph it. So let's start by saying, is it separable? Well, it looks like I could easily bring the y's up here, dx over here, and be able to separate this guy out. So let's just do that. So that's going to say, if I bring him up, that's going to say y squared dy is equal to x dx. Okay, so I was able to separate it. I got all the y's on the left, all the x's on the right. So let's integrate. So it's going to say the integral of y squared dy is equal to the integral of x dx. And we get, well, this guy is nice polynomial, so we use the power rule. So 1/3 y cubed plus c. I'm going to lump all the c's together on the other side, so I'm not going to worry about it. X's antiderivative is 1/2 x squared plus c, where that c represents the combined c from this side and the c from this side. All right, now I really would like to have it in the form of a function if I can get it. So I want to get it in terms of y in terms of x. So let's just go through and solve this guy for y. Solving for y gives y cubed, let's multiply everybody through by 3. So it's going to be 3/2 x squared plus 3 times c, but again, c is just an arbitrary constant, so I'm just going to call that big C. Let's call it C1. Okay, where that c came from 3 times the old c. All right, now to get y by itself, I'm just going to take the cube root of both sides. Plus that constant. And I get that. So this should actually solve this differential equation. Let's try it out. Let me define, let's call it f. X equals cube root of 3/2 x squared plus c. I'm just going to call it c. All right, there we go. Let's check it and see if it works. Let's take its derivative with respect to x. Okay, I get that ugly looking thing. So now let's compute this side and see if we get the same. So I'm going to have x divided by y squared, but y is f of x squared. And lo and behold, I get the exact same expression as I had here. In other words, that thing equals that thing. True. Okay. So it actually is a solution to this differential equation. Let's see what it would look like graphically. So let me go into, let me add a page, add a graphs page, and let's do a, whoops, change it to a differential equation. Okay, again, be mindful, y1. I got to call things y1. So, oh, actually, I don't have any y's on the other side, so I'm good. So I'm going to say, no, I do have y's on the other side. So you've got x over, whoops, sorry, there we go, over y1 squared. Okay. Okay. So there's what the slope field looks like. If I really want to see tighter slope field lines, I can go in and change that. The default of 14 I don't like as well. I like to have it a little more dense, but it slows down computation. Let's go to 20. All right. So that's kind of what the slope field looks like. So you can imagine placing a point at any point in the slope field and then making it hug the slope field, just like the old golf video games in the arcade where you got on the green and those lines kind of told you the contour of the green. Same idea. So in this case, we don't really have any initial conditions, but we could create an initial condition. So let's see, what would be a good initial condition here? How about using something that comes up with a nice, relatively round number? Let's do 4 and 3. So let's say suppose I know that y of 4 is equal to 3. Okay, that's going to allow us to uniquely determine this value of C. Well, let's do the slope field first and just see what it looks like. All right, you plot this and give it an initial condition. So 4, 3. So there we get roughly what it looks like. And it's fairly densely populated because the slopes are not super steep in this zone. So you don't have a big separation between kind of correction points as it adjusts with Eulers method. You can see my initial, right here is my initial point. Notice he's a little bit bigger than the others. There's the initial condition. If I wanted, I could grab him and pull him around and see what the effects would be of the others. Now, what I can do here is I can say, well, I can solve for C by using this initial condition. And then we'll see what it looks like. So solving for C says that 3 has to come out when 4 goes in. So this is going to be 3/2 times 4 squared plus C1 or C, let's call it. So 3 has got to equal the cube root. 4 squared is 16. 16 divided by 2 is 8. So I'm going to end up with an 8 here times 3, which is 24 plus C. Cube both sides. So that says 27 because that's 3 cubed. Cube this side, I get rid of the cube root. So this implies C has to equal 3. So if I actually use this and I plot it with C equals 3, if I plug a C equal 3 in there, I should actually get something that falls right on top of it. So let's try it. The menu, change it back to a function plotter. And now I'm going to put in the cube root of 3/2 x squared plus C, which is 3. And there you can see, plotting it right on top. Pull this guy out of the way. And so you can see the blue guy right there on top. If I hit my tab key, it'll switch to the red guy, which is the approximate. And notice that they're pretty good because the slopes are relatively shallow. You don't have a lot of steepness, so you don't have a lot of deviation that could throw off the approximation. Okay, so there it is. So we're able to solve this guy by hand, and we can actually see that it indeed fits the slope field very nicely. So, separable differential equations, the ability to separate them out allows us to get the function. In this case, we're looking at the cube root of 3/2 x squared plus 3. Okay. Kind of nice. Okay, what we're going to do now is we're going to take a look at the activity that involves a cooling cup of coffee. Here we're given the fact that a cup of coffee is initially at 105 degrees Fahrenheit, placed in a room that is 75 degrees Fahrenheit. And we know that Newton's law of cooling basically says the rate of change of the temperature relative to time. Here I'm using X to represent time. I didn't want to use T like the book does because then I've got capital T and lowercase t, and that can be a little confusing. So I just called X the time. Capital T is the temperature. And Newton's law of cooling says that the rate of change of temperature with respect to time is proportional to the difference between the temperature of the object, in this case coffee, and its environment, in this case 75 degrees. Okay. K is a constant proportionality. So this is just the way things cool. It's really an exponential decay model. The only difference is that instead of decaying towards 0, which a typical exponential does, we want it to decay towards 75 instead. So, for example, if I put a cooling cup of coffee in a room, it's not going to continue to decay until it, hits 0 and continues cooling to absolute 0, right? It's going to actually level off toward whatever the environment is. So this is really how Newton's law of cooling works. Last semester, actually, we cooked a turkey, and we actually did this kind of activity that involved modeling the situation. So anyway, let's take a look at this and see how we can use separable differential equations to solve this guy. So we're going to solve it first, and then we're going to determine the initial value for k, the constant of proportionality, by given the fact that suppose it is initially cooling at 1 degree Fahrenheit per minute, okay, as indicated. So how are we going to find the differential equation here? Let's first find k. Okay, using the differential equation given, we can actually find k pretty easily, because at time 0, we know dt dx, when x equals 0, is -1, because it's cooling. So therefore, that guy will end up being negative. So with that information, we can plug it in here and see what we get. So that's going to imply rate of change, -1, is equal to minus k times my initial temperature of the coffee, which is 105, minus 75. Okay, well, this is a difference of 30. So -1 is equal to -30k. So k is simply 1/30. All right. So we now know k. So that's part A. In the activity, part B says use separation of variables to solve the differential equation and both sides. So let's find all solutions. So here's my differential equation. So I'm going to have k is 1/30 times t minus 75. Okay, so let's try to separate the variables. Well, it looks like we don't have any x's on this side. It's an autonomous, meaning that the only thing over here is the dependent variable. So I'm going to bring the x's over and bring these guys down. So let's see what we get. So it says that dt over t minus 75 is going to equal -1/30 times dx. So now I can integrate both sides. Well, if I integrate this side, this is just going to be a natural log. Since the coefficient of t here is 1, I don't have to do any adjustments like a u substitution or anything like that. So it's just going to be a natural log of this guy. So this is going to say a natural log of t minus 75 is going to equal this guy with respect to x. It's just going to be -1/30 x. Now, in order to get at t, so we want to solve it for t equals something, what I'm going to do is I'm going to raise e to both sides. So if I raise e to the natural log of this, I just get t minus 75. And here I'm going to have e to the, should put a plus c there. So this is going to be e to the minus 1/30 x plus c. again, if I want, I can pull these guys apart and write this as e to the minus 1/30th x times e to the c. And if I want, I can say, let's just call this guy a. And I get a e to the minus 1/30th x. Okay, so therefore, t by itself, let's add 75 to both sides. So t is going to be a e to the minus 1/30th x plus 75. So let's take a look and see what this guy is going to do as x tends to infinity. When you think about it, as x tends to infinity, because this is a e to a minus exponent, okay, it's going to basically be in the denominator getting really large. A is a constant, so this fraction is going to approach 0, leaving me 75. So as x goes to infinity, time goes to infinity, t is going to approach 75, which makes sense because it should cool down to room temperature as time goes on. So that should be as we expect. So let's see what that looks like. Okay, and we'll plot the slope field just so we can kind of see. So here's my differential equation right here. So in this case, because I'm on the plotting menu, I need to call things y1s and so on. So this is going to be y1. So I'm going to say y1 prime equals minus 1/30th times the quantity. I'm going to call this y1. y1 minus 75. And I can even give it the initial condition. I know initially at time 0, it's 105 degrees. So I'm going to put a 0 here for x, that's my time, and 105 there for my y, which is my temperature. And there you see it. I really can't see it too well because it's way up top. So let's bring this guy down. Scroll this guy down until I get there he is. A little further. Okay. Go of it. Okay, so whoops, hold on a second. My connection got lost. Accidentally popped the hat off. You probably couldn't see anything I was doing there. All right, let me see if it finds it again. Sorry about that. I think I found it, maybe. Sorry, I lost the network. Didn't even realize the hat had popped off of my device here. All right, I think I found it. Okay, it's back. All right, so here's what you're seeing. You're seeing the thing level is starting up here and is coming down and leveling off toward room temperature, which is at 75. Now, if we plot this function that we've come up with, we should be good to go. Now, we do need some initial conditions. Right here, we've actually got an a still in here, so we have a parameter we have to solve for. Let me be careful when I put this in my pocket, I don't knock the hat off of it again. So t of 0 is 105. So if that's the case, we can actually solve this guy. Let's just let the cast do it for us real quick. So let's define, we're eventually going to solve this anyway. T of x equals a times e to the minus 1/30 x, and then plus 75. Now let's say solve, t of 0 equal 105 for a. And that gives us an a of 30, which makes sense because if x is 0, this whole thing is 1 because it's e to the 0. So something plus 75 gives me 105. That's going to be 30, which is what I've got. So now what I can do if I want is I can go up here and let's just redefine this guy and put the 30 in. There we go. So now if we go over and graph it, it should fall right on top of that. Let me change it to a function plot. And I'm going to call this t of x. Boom, there it is. So you can see the blue function right there on top of Eulers Method's approximation that we got before, leveling off to room temperature. So here we were able to actually come up with a symbolic form. So we've got the symbolic form, and we can plot it and see it indeed is behaving as we expect. Okay. So this is how basically we can actually come up with a solution to a differential equation by hand and then apply it and make sense of it when it comes to the slope field and the behavior of the physical phenomena we're trying to explore. In this case, Newton's law of cooling. So this summarizes section 7.4, which deals with separable differential equations. I hope you take a look at it. We didn't do activity 7.4.2, I think it was, or 3. One of the ones we didn't do. Feel free to go in and play around with that a little bit, see what you come up with. I do expect you to kind of look at the entire section. We're hitting the highlights here. But work on your homework. If you got questions, let me know. So thanks for tuning in.